Hello, welcome to our second set of notes for the Unit 1 for college algebra. In this section, we're going to be covering, talk about functions, evaluating functions, which means plugging numbers into them, and like look at the main range of functions. So we're going to define those or deal with functions. Functions are a very important part of algebra, so we'll see these come up all semester long. Very last unit, almost to the end of the semester, we'll be working with functions throughout. So functions are going to be coming from kind of relationships or correspondences between numbers. So we'll have two different ways of looking at a set of numbers or two different measurements from a set of numbers and the connection between those. Some examples of functions, things like the number of people coming to a party and the amount of food you need, right? The more people come, the more food you're going to need. The number of gallons of gas you purchase and the total price. A lot of times you buy more gas, you're going to pay more for the gas. These can be represented with equations, like y equals 3.95x. This would be an equation, maybe for the price of gas, right? Because you buy x gallons times 3.95 as the price if it's 3.95 for a gallon of gas, and then y would give you the total cost. It can also be set of ordered pairs. You can have lists like this where you have x values, y values. So how many gallons of gas did you buy? What was the cost? So this would be ordered pairs where each x value would match the y value. Or it could be a graph. You have a graph like this where they show the gallons you're buying, how many gallons at the bottom, and then the price on the side. So this would be the cost and the gallons. And this chart shows again that the more gallons you buy, the higher your price. So these are all different ways to show functions. And so anytime you have a connection between two sets of numbers, you can be dealing with a function. When we're working with functions, we refer to the first set, so like the first set here or the bottom numbers here, the numbers you plug in for x here, those as the domain. So the domain is going to be the first set, your starting set, or your x-coordinates, that's going to be your domain. The second set, the results, the numbers you get out, the cost in this one, the vertical here, those are going to be your y-coordinates. Those are going to be called the range. So the domain, I always think of the domain as where I am, where I start from. That's my domain. The range is your results. It's where you can reach, it's what you can hit. I always think about shooting a rifle or bow and arrow or something. The range is how far I can reach. What can it hit? The domain is where you're starting at. This is where I live, my domain, and then my range is where I'm trying to hit. Okay, so when each element in the domain corresponds to exactly one element in the range, we call this a function. So you can actually make connections between two sets of numbers that are not a function. A function has the rule that every input, so every x value, every starting number has only one output or result. So that's what we call a function. So each thing in the domain has exactly one thing in the range, and that's a function. So down here, I have a couple ways to look at functions. So this first two right here, these are just kind of picture ways to look at a function. You have numbers in the domain, you have numbers in the range. Each arrow here makes a connection, like 2 is connected to 8, 8 is connected to 7, 9 is connected to 15. So those are connections from your domain, your starting point, to your range, your ending point. And we say it's a function if every input, every starting point has only one output. In this case, if you look at this one, you notice that 6 has 2 arrows, right? It has 6 going to both 11 and 15. So that means that 6, going to two different numbers like this means that this is not a function. It's not a function. We don't like to work with stuff like this because in mathematics, you'll be given a problem, you put a number into your problem because you think it's the answer, you try it out, see if it works. Well, if it gives you two different answers when you plug that one number in, now, if you have a second step to your problem or more work to do after that, you go, well, what do I do? Which number do I work with? I don't know. I got two different numbers, and we don't like that. We want to just have one number to work with. So we don't like to work with these. These are not functions. Excuse me. We'll prefer to work with things that are functions. Things like this one over here, where every input has one output. -2 only gives me 10. 1 gives me 6. 3 gives me 6. Now, notice here that we have two numbers giving me the same answer. That's okay. That's actually valid for a function. There is a function that I like to call the boring function. It's a function where it just gives you the same number over and over and over and over again. And that's still a function because every number is giving you just one answer. The problem is when one number you put in gives you two different answers. We don't want that. That's not a function. This one, yes, this is a function. For correctness sake, I probably should get rid of this 8 here because range is what you can get out. And notice we don't get 8, so I shouldn't have that in my. I need to take that out of my example because the only numbers you can get are 3, 6, or 10. So this is a function. Take out that 8. Again, because each input has only one output. Now this was a graphical kind of picture way to see it. We can also look at ordered pairs like this, so sets of ordered pairs. Each one of these, is an x, y, right, an input and an output. We always think of the x's are inputs and the y's are outputs, or x is our first number, y is our second number. And we can look at these, and actually these can be functions too, because you can look at this and say, okay, 0 goes to 9, so that's one connection, 0 goes one place. 10 goes to 6, 20 goes to 11, and 30 goes to 13. And since each of these go to a different number, and we don't have the same number going to somewhere twice, this is a function. So that set of ordered pairs is a function. What about this one over here? We have 12 goes to 9, 7 goes to 9, 11 goes to 14, 13 goes to 15, 21 goes to 14. That one is still a function. And I know you might have been thinking not because of the 9s here or the 14s there. Remember, just like up here, it's okay to go to the same number twice. What's not okay is one number going two different places. So this one's actually a function. So you're wondering, okay, what would it look like if we had a set of ordered pairs that wasn't a function? Well, a set of ordered pairs that's not a function would look like this. You might have, 1 goes to 3, 2 goes to 4, and then you might have 1 goes to 5. And this would not be a function because 1 is going to two different results. We have 1 going to 3 and 1 going to 5. Since that input 1 has two different outputs, this one is not a function. That's what we're looking for. We don't really care about repeated last numbers. We care about repeated first numbers. If you have one input that has two different results, 1 goes to 3 and 1 goes to 5, that makes it not a function. We don't want to work with that. That's not fun because now when we use this function, you put 1 into this function, 1 is an input, 1 is a starting number. You get two different numbers out. You go to graph it, now it's going to have at 1, you're going to have two different values up here in the chart, and that's not great. We don't want that. We want kind of this nice straight line kind of thing going on, or it might not be perfect straight, but we don't want two different values to go to. Okay, now if we're working with functions, we'll typically work with functions in equation form. Lists of ordered pairs are great, but when you get to millions or billions or even infinite numbers that you want to work with, it's not great to work with list of ordered pairs or pictures. So we'll usually use an equation. When we write equations for functions, we can write them with y equals, but most of the time we'll write them with f of x. The reason we use f of x is because by writing f of x here, you tell everybody that this equation is a function. So this is just a way to say that this is a function. And now I know you might be looking at this and thinking this says f times x, but that's not times. In this situation, when you have equals and you just have x next to x, with f next to x without parentheses, this is called f of x. And this is actually the label for a function. So the f here is your function name, and the x inside the parentheses is actually your input or starting value. Now, I told you usually x is the end starting value. That's usually true. That's why you usually see x inside here. But since functions get used in a lot of real life situations, the x doesn't have to always be x. If I'm doing a function that deals with weight, you put in the weight and then you get something out of it, then it might be w. Or if it's height, you might be h. So it can be all kinds of things. You can have lots of different letters instead of x in here. But this f and x is kind of the go-to. Mathematicians, we like to use x for a variable, so we use x here. We like to use f for function, but you can't figure out why. So that's why this is f and that's x. So this is just the way to say this function, you put in x, and it's going to give you some result. And that's the main thing we do with functions. The primary thing we do with functions is we plug numbers into them and get out results. We call that evaluating. Evaluating is you plug a number in. So when we evaluate here, we're going to plug a number in. Now, instead of having to sit there and say plug in such and such a number and get the result, we'll use this notation right here. This notation, where you see f and the -2, is telling you plug in -2 for x. And, see how that's so much nicer. I would hate to have to write this every single time I wanted to tell someone to plug in -2. So instead, I just put this, f of -2. That tells me that for this function we have right here, they want to replace all the x's with -2's. So I'm going to take all these x's in this function and replace them with -2's to find f of -2. We're evaluating the function we're plugging in -2 for all these x's. So I get -2 squared. Make sure the whole -2 is squared, because it's got that power on it. Minus 3 times, remember you have your number next to a letter that you're multiplying, so 3 times -2 plus 4. Now you can throw this in a calculator, get an answer, that's fine. I'm not going to stop you. You get a calculator for the test, so that's a great habit to get into. I'm just going to do it by hand real quick because it doesn't really need a calculator, but if you want to do it in a calculator, that's fine. So -2 squared, remember when you square a negative, you get a positive. So it should be positive 4. If you type this in a calculator -4, you forgot the parentheses. So don't forget your parentheses and type negative to the power, because otherwise you get the wrong answer. -3 times -2, well, double negative makes a positive. 3 times 2 is 6, plus 4. Yeah, 4 plus 6 is 10, plus 4 gives me 14. So this is my output. So my input was -2. I plugged that into the function. Output was 14. If I think about those arrows, I think I have an arrow that goes from -2 to 14. Or if I want to do ordered pairs, I have an ordered pair that was -2, 14. You know, that's the connections. What we're really looking for in this problem is just the 14. They just wanted us to find out what you get if you plug -2 in. But you know, notice that's what we're doing. We're actually figuring out what the arrow goes to, or you know, what the ordered pair would look like. We know that if you plug in -2, that's your x. And your y, your result, is 14. Again, this f of x, you could replace this with y, the whole thing with f of x with y, and the equation will work just as well because your output you get, the answer you get is y, the input is x. The reason we use f of x again is because that notation is good for this kind of situation. It tells people it's a function. Not every equation has a y as a function, so it's nice to let people know. When you put f of x or g of x at the beginning of the function, people know it's a function. Okay, let's do the next one. So we got g of x this time is this equation, and they want us to find g of 3. Well, g of 3, again, that means plug in 3 for x. So we're going to replace this x with a 3, just like they did here, right? They took the x here, they replaced it with a 3. So that's what we're going to do. We're going to replace the x with a 3. So to find g of 3, replace this x here. So we have 2 times 3 squared plus 5 times 3 plus 2. All right, so we replace those x's with 3's, and then we do our calculations. Remember, if you're doing this by hand, order of operations, you always do powers before you multiply. I always get people trying to take 6 squared, but no, you have to do the power first, because powers go before multiplication. So I do 3 squared is 9, so I get 2 times 9. 5 times 3 is 15, plus 2. Well, 2 times 9 is 18, so I get 18 plus 15 plus 2. I teach math for elementary teachers, and one of the tricks we talk about is when you add numbers like this, you always add the ones that are easiest. So I'd take 2 plus 18, get 20, and then add 15. 20 plus 15 is going to give me 35. That's one of those little tricks for math that you can do, because addition, you can add any order you want. So I just add 2 plus 18, get 20, plus 15 is 35. And again, you can type this in a calculator, that's fine. No problem with that. So this tells us that if you plug in 3 to this function, you get 35 out. So if I had my arrow again, my arrow would go from 3 to 35. And I have an ordered pair, right? My ordered pair would be 3 comma 35. That would be the ordered pair for this function. So again, they just want to know what answer was, what the y value was, what the result was. I'm just talking about, this tells us these ordered pairs. That's what those are. The arrows, the ordered pairs, it's just a connection between that number and that result. The function got us that same connection. Now, there is no rule that says the only thing you can plug into functions is numbers. You can plug expressions, things with letters and numbers, or just letters or just numbers, into a function. So this last one here, we're going to take it, we're going to plug all of this in there. We're going to plug in a minus 4. So instead of just plugging in the, a number, we're going to plug in this whole thing, a minus 4, for every x. So every time we have an x, we're going to replace it with a minus 4. So this function is going to become, f of x is going to become f of a minus 4, because we're replacing x with a minus 4. Now this x squared becomes a minus 4 squared plus 2 times a minus 4 minus 3. So we plug that in. Now, with this, we're not going to get a final answer because we don't know what a is. This one is not going to give us a number at the end. We can simplify this a little bit. We can get rid of some parentheses and stuff, so we can kind of make this better. But we're not going to get a final answer out of this. We're not going to get a number because we replaced letters with letters. If you do that, you're going to get an expression. You're not going to get a final answer, not a number. Now to do this, first off, I'm probably going to do the easy stuff first. I'll start with this distribution, right? Whenever you have a number multiplied times parentheses, you can distribute. So you get 2a minus 8, right? 2 times a is 2a, 2 times 4 is 8, still minus 3. Don't forget the minus 3 out here. Over here, I have a minus 4 squared. Remember, when you take a quantity like this, a subtraction like this, you can't just square both parts. That's one of the biggest mistakes college algebra students make, is they try and square the a square the 4 and call it good. No, it doesn't work that way. When you have a minus 4 squared, you actually have to take 8 minus 4 and multiply by itself like that. That's what it means when you have a parentheses squared, is you're multiplying that thing times itself. And hopefully you recognize this. This is something you've done before in like pre-college algebra or in high school. This is when you actually have a FOIL problem, right? FOIL is where just a fun way to remember how to multiply these. You know, we do firsts, a times a gives me a squared. We do outside, a times minus 4 gives us a minus 4a. Do inside, which is negative 4 times a, which is another minus 4a. And we do last, negative 4 times negative 4, which gives us a positive 16. Now, you'll notice that if we just squared the first term and squared the last term, we would have got these two, but we would have missed the middle, because when you have negative 4a and another negative 4, you actually have a minus 8a in the middle. So that's actually our expression. Our expression is a squared minus 8a plus 16. That's the answer we get when we take this a minus 4 and square it. So you need to multiply it with itself. You can't just square both parts. It doesn't work. Sadly, it'd be nice if it did, but it doesn't. You have to multiply it out. So I use the FOIL technique. There's other methods, but that's the one I see a lot. So a squared minus 8a plus 16. And then, of course, we want to go ahead and simplify this. We're going to combine some like terms. So I've got that negative 8a and a positive 2a. So that gives me a minus 6a, negative 8 plus 2. Got 16, negative 8, negative 3. 16 minus 8 is 8. Minus 3 is 5. So plus 5. And then don't forget the a squared at the beginning. So this is the final answer because it's as simplified as we can get. I know some people look at that and think about factoring, breaking it up. You don't need to. We are fine leaving it like this. This is simplified. Here we didn't really like having all these parentheses. That's why we got rid of those. But this, I think, would be the final answer. That would be f of a minus 4. And again, we don't get a number answer because we put a's in there. We don't know what a is. So our final answer is going to have a's in it, and that's fine. When you throw letters in, expect to get letters out. That kind of makes sense, right? When we threw just a number in, yeah, we just got a number out, and that's why it worked that time. But since we threw an expression with letters, we just got another expression, another formula out. Okay, so that's a function. You will evaluate a function by plugging things into it. Whether it's numbers or expressions, you're plugging things into it. Okay, let's talk a little bit about graphing and functions. Now, functions are the thing we graph. When you graph in a college algebra class, when you graph in your algebra classes in high school or remediate algebra class or intermediate algebra, anything like that, you're graphing functions. So anytime you have a function like this, you can graph it. To graph it, you're going to graph the x, y pair. So on the graph here, you're going to draw every pair of numbers, where you know what x is, you know what y is. Now, we don't have any x, y pairs to start with. So one way to get x, y pairs from a function like this is to make a x, y t-chart. Instead of y, I'll put f of x because we know that the result, the answer, y is going to be f of x. So a lot of times my math app and stuff will write it like this. We'll write x and f of x. And I'm going to pick numbers to plug in. I'm going to pick things that I think are easy to put in. So I usually pick small things like 1. 0 is a nice, easy thing to plug in a lot of times. Sometimes it's good to plug in negatives. So if you have a function you're not familiar with, it's good to plug in some negatives. And I'm just going to plug these into this function and find out what the results are, and that helps me draw my function. So if I plug in 1, so I do f of 1, I get 1 cubed minus 2 times 1 squared minus 5 times 1 plus 6, and I get something like that. And I simplify it. 1 cubed is 1, 1 squared is 1 times 2 is 2, so I get minus 2. Minus 5 times 1 is minus 5 plus 6. Simplify that a little bit more. 1 minus 2 is a negative 1. Minus 5 more is negative 6. Plus 6 is actually 0. So at 1, I get 0. And then I can keep doing that for all of these, right? I can plug 0 in. F of 0 is a pretty easy one, so we'll go ahead and do that. 0, 0 is cubed. That's 2 times 0 squared. Minus 5 times 0. Plus 6. And again, 0, it just kills stuff off. So that's 0, that's 0, that's 0, right? 0 times cubed, 0 times 2, 0 times 5. All we're left with in this case is just 6. This one just gives me 6. So 0 gives you 6. Now this gets pretty old fast. So if you're like me, you're looking at it and going, I don't want to do that. That's just annoying. That takes time. It's not that much fun. I guess maybe I kind of like it because I'm a weird math nerd and I think it's fun to do powers and multiplying all that. But if you think this is kind of boring, you'd rather do it a faster way, well, that's why I told you you probably want a graphing calculator for this class. There's lots of situations where a calculator will help you out. I'm going to use the TI-84 plus CE for all my examples. You don't need a plus CE. I just like the plus CE because it is a color calculator. It has a nice backlit screen, so it shows up good when I'm doing these videos and stuff. Any TI-84 plus is going to do pretty much everything my calculator does. If you have a TI-83, I'd say like 90–95% of what we do, the TI-83s will do as well. There's a few little things later in the semester that your TI-83 might not do. Probably not a big deal. If you're a confident math student, you'll be fine with the TI-83. If you're not super confident, if you really struggle with math and you want the easiest job of it, I kind of recommend giving you the TI-84 Plus because that's going to be exactly what I have. It'll be the same calculator, so you'll know exactly what buttons to press and all that. So that'll just make your life just that much easier. If you have any other kind of graphing calculator, Casio or whatever, that's fine. I have nothing against those. I just use the TI-84 Plus because it's kind of the common one. Most people use it, so I just wanted to be like everybody else so that you guys hopefully would have the same calculator, so there's not a lot of learning curve and stuff. Okay, so to graph this on the calculator, I'm going to go into this y equals button, so that y equals button at the top. I'm going to type that in. I'm going to type in x. To get the cube power, I'm going to use this up arrow right here. I call it the caret key. It's your power button, so that caret key right there. So get x to the third, so x to the third. Let me use my right arrow to get out of that, because if you keep typing in the power, it kind of mixes this up. Do my minus button, my 2, the minus 2. Use this x again. I know this says x, t, theta, n. This is really the variable button, and it's only ever going to make x's unless your settings are messed up. If it's doing t's, thetas, or n's, someone messed up the settings. You should probably go back and kind of factory reset the calculator, and then you can just have it do x's like minus. To do the squared, you can use the caret key again. You can use the power, or there actually is a squaring button right here. So if you're squaring, you can just use that squaring button. We use a lot of squares, so it's nice to have that squaring button. Okay, minus 5 times x. And plus 6. So I'm just typing this in just like it looks over here. And the nice thing about doing that is now I can sit there and just graph it as is. So if you want the graph, that's probably the easiest way to get the graph. Now, if you're doing a MyLab homework question where they tell you to fill in a t-chart, well, this doesn't give you a t-chart, right? But if you hit second, before you hit graph, it does second, makes you do the table option instead of the graph option. And then it actually gives you a table of values. Now, my table, I'm like way down at 11 for some reason. So I'm going to go back closer to 0. And you see at 0 there, I got the 6 that I got. At 1, I got 0. You can see if I go back to -1, it also gets 8. Well, that's way big. -1 is 8. What else do I have here? You can see that at 2, it gives -4. So see how much easier this is for filling in the chart. You just make the calculator do the work for you. 3 gives you 0. And there we go. That's a lot of numbers. This is probably enough to fill in the rest of my chart, or my table, or my graph here. So again, your calculator will do this, and it's a really great tool to just use the calculator for this. Okay, so at 1, it goes up 0. At 0, it goes up 6. It's going to be all the way up here. And -1, it goes all the way up to 8. So like if I think 7, 8 is all the way up there, so -1 is all the way up there. 2 actually gave me a -4, so 2 is all the way down here. 3 gave me 0. Do I have more values? After that, it gets too big, so I can't really go any further. Oh, here, looking back, notice that -2 is 0. That's probably another important point to find there. So I'm going to put -2 and 0. So -2 actually hits 0 right here. And then, when I graph this, I can kind of look and see. I should be getting a picture like this. I can see that if I come up here and hit that point up there and then come back down and -2 goes like this, you can kind of see it looks like this. Again, I'm graphing by hand, so it's not going to be super pretty. But by finding enough points, you can make any graph. This is kind of your fallback fail-safe. If you ever don't know how to graph a function, you can just sit there and find enough points on your graph and you can get a picture of it. So that's a tool you can do. Okay, so this is our graph. This is our function. Now this function has a domain and a range. So we talked about domain again. Domain is the x values or inputs. A function, when it's graphed like this, you can figure out its domain because the domain is how far left and right it reaches. So what x values does it work on? So like I can plug in -1, I get a value. I can plug in 0, I get an answer. Plug in 1, I get 0. Plug in 2, I get definiteness. So this function here has a value for all numbers going left and right, because you can see how this line is going down forever. It's going out further and further. It's pretty steep, but eventually, if I want -5, I just have to go down far enough, and there's the value. So I can actually get the domain for this. The domain is going to be all real numbers from -infinity to infinity. And to write that, to write domain in negative infinity to infinity, we're actually going to use what we call interval notation. Interval notation is where you just list the starting and the stopping numbers for this. Well, since we're going from negative infinity to infinity, start with negative infinity and go to infinity. And then when you work with interval notation, you always use parentheses or brackets. We use brackets for numbers we get to, we reach. And we use parentheses for numbers that we don't quite reach. Since you can't reach infinity, we always use parentheses for infinity. So this would be the domain, and this would be what we call interval notation. So that's interval notation right there. Range will do the same thing, but now we're going to go up and down. So this was our x's. This will be a y's. Again, xy graph. So x's are horizontal, y's are vertical. So now we're thinking up and down. How far does it reach up and down? Well, you can see this arrow is going down forever. This arrow is going up forever. So this reaches up and down forever. So this range for this one is also negative infinity to infinity. A lot of functions will have that. That's very common with functions. A lot of functions, you plug any number you want in, you'll get an answer out. And it can give you answers anything from negative infinity to positive infinity. I'm going to do one more function. This one doesn't have everything you work for domain range, so we're going to work with that one. So this is this function here, f of x is absolute value of 3x minus 6. Remember these two bars like this, that's the absolute value bar. What those do is they take the answer and make the answer positive. So whatever your final answer is, they'll make it positive. They don't change stuff in the middle, so we're not going to change that minus to a plus. Absolute values never change the sign in the middle. They take the answer to the problem and they turn that into a positive. That's what absolute values do. So I can do another t-chart for this. And this one's actually pretty easy to do. If I do x and f of x, again, I put nice easy numbers, things like -1, 0, 1, maybe 2, stuff like that. I can see what this looks like pretty easily. -1, so f of -1, which means I put 3 in, -1 in for x, so I have 3 times -1 minus 6. 3 times -1 is -3, minus 6 is -9, and the absolute value of -9, absolute value, because at the end, when you get the answer, you take the absolute value, that turns that positive, so that gives me 9. I put 0 in there, I get 0 minus 6, absolute value -6 is 6. Plug a 1 in there, I get 3 minus 6, it gives me -3. That's the value of that is 3. And again, if you can't do this in your head, that's fine, because you can type this in your calculator. So if you want to get these t-charts and you don't want to do it in your head, you don't want to have to write it all out, you can just type this in your calculator. Now to type an absolute value in your calculator, there is a math button here. It's one of our favorite buttons on this calculator, this math button. It has lots of cool options on here. If you scroll down all the way to the bottom of this first option, you'll see, oh, I'm forgetting wrong. It's actually not down, it's over. I had a brain part there. So under number, if you scroll to the right, you'll see there's ABS, and that stands for absolute values. Hit enter on that. It'll put in absolute values for you. And then you can just type inside. So, I'm going to type in my 3x minus 6. Make sure you're using the minus and not the negative. There's a negative down here that's different than your minus. You only use this if you want to make a number negative. You use this when you're subtracting. So you get 3x minus 6, hit enter. So now it's typed in there. And then I'm going to hit second table. Second again makes it do the table. And there's those table values. So now I don't have to do it by hand anymore. I could just look at this and see, okay, -1 is 9, like I said. 0 is 6, 1 is 3, 2 is 0. If I keep going, you'll see here that 3 is 3. So that's another one. So I can do 3, 3. And that should be enough to kind of get a picture. So I can do -1. I'm way off the chart. I might even skip that one. 0, I get 6, which is right there. 1, I get 3. 2, I get 0. 3, I get 3. And so you can see if you did 4, I think, yeah, 4, you get 6 again. It goes up here. 4 is 6. There's another one. You can see that it actually makes this V. It's a straight line V, not curved. That's just a bad drawing right there. It looks like this. That's what absolute values typically do. If you graph the absolute value, you'll actually see them mostly make these big V's. They might be upside down sometimes. We'll talk about why that happens later. But yeah, absolute values kind of make this V shape. What happens is basically all the negative answers you got would normally got flipped up and be positives. And so it makes this V shape where everything has to stay positive the whole time. Okay, so let's go back to domain and range for this function. Again, domain is the x's, right? Domain is the x's. So if I think about how far left and right does this reach? Again, I'm not talking about where it crosses the intercept. I'm talking about how far left and right does this function reach? Well, since it's going left forever, going right forever, this thing is going to reach forever, left and right. So this is also going to have negative infinity. You can plug any number you want in here for x. Everything works for x. So the domain is negative infinity to infinity. But this function only ever gives me numbers 0 or bigger, right? It can't give me negative answers out. So the range, remember range is the y values, it's the up and down. The range for this starts at 0 and only goes up. It doesn't go down to negative infinity. So we're going to start from 0 and go to infinity. Infinity is always parentheses. But since we actually reach 0 here, we actually can reach a 0. We don't miss it. We're not close to it, but we actually reach it. We use a bracket. We always use these square brackets for numbers you reach. We use these absolute values, this parentheses for numbers you can't quite reach. So that would be the range for that function. A couple more I just want to show you. These are some interesting functions you'll see. And it's good to talk about their domain and range. This one right here, this is what I mentioned earlier, that's that boring function where it just keeps giving you the same answers. This function, no matter where you look, you always get 2, because it's always 2. So this is the constant function 2. Its domain, what can you plug in? Well, since it goes left and right forever, its domain is still negative infinity to infinity. That's a pretty common domain. You'll see that a lot. The range here, though, is only one value. The range is always 2, because left and right, it's always giving you 2. So the range for this is just 2. Now, how do you give just one number for range? Well, we usually use what we call roster method. So instead of using these intervals like this, we'll just put curly brackets like this. And that is just the set of one number. Whenever you have a small set, just a couple numbers, you're not doing a list of infinite numbers from negative infinity to infinity or 0 to infinity, you'll just use roster method. So the only answer we can get is 2. Nothing else. You can't get anything above or below 2 because it doesn't go up or down, it just goes left to right. This one, you'll notice here, this one does not have arrows. This one has ends on the graph. So here, I'm going to put little dots there just to show you that it has ends on the graph. This one stops. It doesn't go off to infinity or negative infinity. So this one, we look at domain, we're not going left and right forever. We're going to start at negative 3. So it's going to start at negative 3 and go until we hit 4. So at 4 is where it stops. I put a filled in circle, so I'm going to say it actually has a point here at each end. If I did a big open circle, that means I don't quite reach it, but I'm going to just put a filled in circle. So here, these we're going to put in a bracket because we actually reached those endpoints. Again, that's your x values, right? That's x's, that's why it's negative 3 and 4. If I do the range, that's my y's up and down. So in range, you can see you start at negative 2 and you go until you hit 3. So the range, you're going to start from the bottom. When you range, go up to the top, so negative 2, 3. And again, we hit those values because it was filled in circles. That's going to be our range. So those are kind of some of the things you might see on the homework and stuff. Interval notation like this is something you should have seen in the past, so hopefully it's not super new to you. We'll use it a lot this semester, so you probably get a lot of practice with it. It'll show up. You'll need to use it on the exams. If you're really not sure about it, you might want to look up, just do a little Googling interval notation. Make sure you're really familiar with it because it's something we'll use a ton of. Okay, a couple more things to talk about with graphing. We're getting close to the end. So the next thing is what we call the vertical line test. The vertical line test says that if you have the graph of a function and you draw a vertical line, you should only be able to cross it once. If you cross more than once, it's not a function. That's what the vertical line tells us. So if a vertical line, straight up and down line, crosses more than once, it's not a function. So this first example here, right here, this graph, if I drew this graph, I'd look at this and say, wait, I can draw a vertical line up and down, crosses twice, so it's an up and down line, crosses twice, so this was not a function. So no function will ever have a graph that looks like this, look like a little ellipse or eyeball or something like that. That won't happen. That's not a function. We'll always graph functions, so we'll never graph anything that looks like this. Next one, you'll notice if you draw a vertical line anywhere on here, it passes, right? It only crosses once. So this one, yes, this is a function. These straight lines, we saw that kind of the first section. You'll see this more again later. These are the y equals something with x lines. These are always these diagonal lines are going to pretty much always be functions. This next one, you probably recognize this. This is called a parabola, where it's a curve like this. We'll talk a lot more about these later on in the semester. Again, if you draw vertical lines here, anywhere you draw it, anywhere you draw a vertical line, you're only going to ever cross this parabola once. So that means it's a function because it doesn't cross more than once. So yes, this one is a function. This last one here, this is actually part of what we call a hyperbola, where it's curved like this to the side, stuff up and down, that's a parabola. This one, oh, sorry, my phone went off. I thought I had that silent. Okay. This one does cross twice again, and because it crosses twice, it is not a function. So again, if you cross twice, you are not a function. The reason this is because if you can pick one x value and find two y values that go with it, then it's not a function. We said that, remember that every input, every x, can only have one y. If you have a place where x has two y's, it's not a function. So this is not a function. All right, next thing to talk about with graphing. So you can actually use the graph of a function. This is what this is. This is a graph for a function. It passes that vertical line test. So it is a function g of x. You can use a function to evaluate, or a graph to evaluate the function. You can actually look at this and figure out, okay, what's the answer going to be? The trick is to remember that the number I'm plugging in is always going in for x. So if I think about -6 being my x, I can think on this that my x is going to be -6 and ask what the function's output or y value is there. So if I look at that -6, I see that right here, my y value is 3, right? 2, 4, I got 3 in between. So the output, the y value, is 3. So this function, if you plug in a -6, you get 3 as your y. It's that ordered pair, right? The ordered pair -6, 3. So that tells me that -6 goes with 3. Try the next one. If I do 0, well, 0 is right here, right? 0 is in between 2 and -2. There's 0. This one is 0 high, so I actually get out 0. If the x is 0, the y is also 0 in this case. Try the last one here, 2. If x is 2, so looking at x is 2, so 2 over, and what's y? Well, y in this case is -3, so I get out -3. That's my y. So we can actually evaluate these functions if you have a graph of the function. If you look at a specific spot for x, what the result's going to be for y, that's your output. Okay, now when you're working with functions, we're going to work with those domains and stuff. You have to watch out for some things that you got to be careful with. So if a function is defined with an equation, so here's a couple functions, they are defined with equations. The domain, again, is all the numbers you can plug in where the function works, where you get the output as a real number. So there are going to be certain things you have to be careful about, certain things that are going to be, cause problems. The first one is going to be fractions. Why do fractions cause problems? Because fractions can never have 0 on the bottom. Remember that if you have 0 on the bottom of a fraction, you divide by 0, that's not allowed. There's no thing in math that lets us divide by 0. Divide by 0 does not work. If I think about, if I have 5 objects and I divide it by 0, that means I'm trying to take 5 things and put them nowhere. And you can't do that. You have to put them somewhere. So we're not allowed to divide by 0. So with functions like this, where they have fractions, we have to think about when would the bottom cause problems? What do we have to avoid? Well, first thing we have to avoid is we have to avoid -4. Because here, if I try and do f of -4, I get 1 over -4 plus 4. And -4 plus 4 is 0. So I get 1 over 0. And that is not allowed. This does not exist. The fancy math name for that, we call that undefined. This is undefined. There's no value for which you can divide by 0. You can never do that. It's undefined. So we'd say that this does not work. So this does not give us a real number. So we can't use -4. So -4 is not good. Now, 3 would have been fine. I could plug 3 in here because if I do f of 3, I just get 1 over 3 plus 4, and that's 7, and that's fine because 1 over 7, that's a fraction, right? 1 divided by 7, that's a nice fraction number. It's nothing big deal. So that's real. That one's real, but this one is not. So when you're doing fractions, you always have to be careful. Watch out for numbers that try and make it undefined, make the bottom divide by 0. The other thing you have to be careful is with roots, like this guy. So we have a square root here, square root of 2 minus x. Because remember, square roots only work on positive numbers. A square root, remember, says what times itself gives you this number. So these are only going to work if the stuff inside of here is going to be positive, because you can't take the square root of a negative number. So let's try, let's see. If I plug -4 in here, does that work? So if I do g of -4, I get root 2 minus, well, x becomes a -4, and then that's all -3, because that's on the outside. But if I do 2 minus a -4, that actually becomes plus, right? Double negative becomes plus, and that's okay, because you can square root of 6, that's a positive 6, and so that's okay. That's a real number. That's fine. That's real. So it's actually not -4 that's the issue at the time. It's actually going to be the 3 that's the issue. If we try g of 3, we'll see that that's the problem here. Because here, if I do 2 minus 3, and then subtract 3, well, 2 minus 3 doesn't work because that gives us a negative. 2 minus 3 is -1. And you can't square root -1, because what times itself is going to give you -1. You know, if you do 1 times 1, you get 1, not -1. You negative 1 times negative 1, you get positive 1, right? So double negative is positive. So this does not work. This is not real. So this is imaginary. It's not real. We'll talk more about what imaginary means later. For now, you don't really need to know, except for the fact that it's not real. So this one doesn't work, just like that one didn't work, because those are not defined. So when you're looking at the domain of functions, when they give you equations, always watch, is there fractions in the equation? Because if there's a fraction in the equation, you got to worry about the bottom being 0. Now 0 wasn't the problem, right? We didn't throw 0 in for x, we threw a negative 4 for x, because it's whatever number makes the bottom 0. And then again here, when you have roots, you always worry about, what is going to be a problem, because when you plug it in for x, it tries to make you square root of negative. You can't square root of negatives. So when you're thinking about domain, those are things you have to watch out for. Okay, last page, last thing I want to do, we are going to actually give the domains for some of these fraction equations like this. We're going to figure out what the domain is. So to find the domain of this function, I got to figure out what numbers make the bottom equal 0. Now this one's not very easy to figure that out because it gives us this quadratic on the bottom. So what I do to figure this out, what's going to make the bottom 0, I'm going to take the bottom, I'm going to set it equal 0, and I'm going to solve that. I'm going to say, okay, figure this out. Now, we'll talk about a lot of techniques to solve this later, but at this point you've probably seen at least one technique. And one technique for solving this is to factor this, what we call quadratic. This is the common technique for solving a quadratic, is you just take this quadratic and you write it as a multiplication. What do you multiply to get this? And remember, when you multiply to get x squared, we're going to have to multiply two x's to get x squared. And you multiply to get 20, we're going to have to think of a few things that multiply to give you 20. But we also have to worry about that 9 in the middle. So remember that we're going to multiply for 20, but we're going to add for 9. So we're going to think about two numbers that you multiply for 20, add for 9. Like 2 and 10 multiplies for 20, but they don't add for 9. What else? Well, 5 and 4 multiply for 20, and 5 plus 4 can give us 9. So we're going to look at 5 and 4, because 5 times 4 gives me 20. And if they're both positive, 5, positive 4, you multiply, you get positive 20, and you can add, and you get positive 9. So that's actually how we factor. That's called factoring. We just factored into this expression. And we do that because the rule is that when you multiply and get 0, one of these two parts has to be 0. So either x plus 5 is 0, or x plus 4 is 0. One of those has to be true. If you're doing this, one of those two things has to be true. Okay. So either x plus 5 is 0 or x plus 4 is 0. So if I set this equals 0, I subtract 5 across. I see that x equals negative 5. That would give me 0. Subtract 4 across, I get x equals negative 4. And those are the two numbers that would give me 0. If I put a negative 4 in here, negative 4 plus 4, that's 0. This 0 multiplies times negative 0. Negative 5 in here, negative 5 plus 5 is 0. Multiply, you get 0. So if you plug either one of these numbers into this expression for f of x, so you plug in negative 4, negative 5, it makes this 0 on the bottom, and it's undefined. We don't want those two numbers. So to write the domain for this function, we're going to write everything except those two numbers. We're going to put everything but those. So that means we're going to start from the smallest I could possibly get, which is negative infinity. I'm going to go along and include all the numbers until I hit the smallest one, which is negative 5, that I don't want to use. I don't want to use negative 5. So what I'm going to do is I'm going to put negative 5 here and a parenthesis. Remember, the parentheses means you don't touch it, you just get really close. So this is all the numbers smaller than negative 5. Negative 6, negative 7, negative 8, negative 9, all those numbers are in this set. Negative 5.1, negative 5.001, all those numbers are less than negative 5 are in this set, but negative 5 is not included. That's why you have the parentheses here. And then I'm going to use the next set, and I'm going to start on the other side of negative 5. So I'm going to go for negative 5 from the other side and do all the numbers bigger until I hit my next problem, which is negative 4. So I want the numbers between negative 5 and negative 4. Again, I don't want to include negative 5 or negative 4, so I'm going to use parentheses. So I've got the numbers between. So this would be like negative 4.5, negative 4.75, negative 4.85. Those are all numbers that are between these two. So those are the numbers I want to include there. I didn't include negative 4, and I didn't include negative 5. Last time, I'm going to go from negative 4, keep going until I hit forever, right? Because there's no more problems. We already got the two problems done. So those are the issues. So this is my domain. Now it's got 3 pieces to it. So we're going to use a symbol here. This is called the union symbol. And the union symbol, we use that union symbol to put the sets together. So we're putting this set together, we're putting these sets together. Union just puts it all together and gives us one big answer. Oops, like that. So that would be our answer. This is the domain, because it's all the numbers we can use. We just took out the two numbers we couldn't use, negative 5 and negative 4. That's what we removed. Let's try this one more time just so you get the idea. Again, anytime you have a fraction, we look at what makes the bottom equal 0. Those are the things we pull out. So I pulled out -5, I pulled out -4, and I left everything else from -infinity to infinity. I cut out those numbers. That's why there's parentheses here, because I cut that out. It's missing stuff. The -4 and the -5 are missing. Okay, let's try the next one. Here again, I've got a fraction, so I'm worried about the bottom equaling 0. Again, it's a quadratic like this. I'm going to have to factor it. A little bit of factoring here to try to figure out what makes that equal 0. So to factor this, again, x times x gives me x squared. I need to multiply for -6. I need to add +1. Multiply for the last number, add for the middle. This time I'm thinking 2 and 3 will multiply for 6. And in order to get the +1 here, I'm actually going to make one of those numbers negative. So I'll subtract. Since I want a +1, I'm going to make the 2 negative and the 3 positive. That way when I add those, you get +1. But if you multiply those, you get -6. So now I can see that x minus 2 equals 0 is going to be an issue. X plus 3 equals 0 would be an issue. If I add 2 across, x equals 2 would be a problem. And subtract 3 across, x equals -3 is a problem. So those are the two numbers I'm going to pull out this time. I don't want -3, and I don't want 2. So what I'm going to do is I'm going to find my domain. Again, I'm going to start from -infinity and go until I hit infinity on this end. And I'm just going to take out 2 and -3. So first off, I'm going to take -3 out first because I don't want -3. That's a smaller number. So I'm going to jump -3 on the other side. I'm going to include the numbers between -3 and 2. So I'm going to go between -3 and 2. But again, I'm going to not include 2. And then the other end, I'm going to start from 2 and go until I hit infinity. So I got 3 pieces again because I took out -3, I took out 2. That's what I cut out. Again, I'm going to use union here. Union, it looks like a U, but no tail. There's actually a button on my math lab that gives you the union symbol, so when you need it, you just use the button on my math lab. But that's the union symbol. It just puts all these groups together. It's kind of like glue. Just glues them together. So it's this set plus this set, put it together. And so that's our answer, because it's all the numbers that don't include 2, because 2 is missing, and -3, because -3 is missing. And that's the domain. We'll see domain come up more throughout the semester. We'll see a lot more equations with these x's on the bottom that we'll work with as well. This is something you'll see come more often as we go. But you should be able to write that domain where you took out these numbers we don't want. And that's it for this function, this set. So we're working with functions. You should be able to plug numbers into functions, evaluate the functions. You should be able to use that vertical line test to see if something is a function from the graph. And then you should be able to talk about the domains and ranges of these functions. Domains here is a big deal you see when you have to worry about fractions, stuff like that. Okay, that's it for this set. So hopefully that helps you get homework 2 going and you really understand that. As always, you can always email me questions, ask me questions, use the Ask My Instructor button. And hopefully you're having a great semester, and we'll see you on the next one.